Communications for a Connected Sky. This is from Professor Fan Hu, Professor of Wireless Communications Engineering in the School of Engineering, Design and Technology at the university, and has been since 2005. She received a first-class BSc Honours degree in Mathematical Sciences and a degree in Information Systems Engineering, both from this university. Professor Hu has received considerable support from UK funding councils such as the EU, the European Space Agency, and so forth. She is the author or co-author of 3 books and has written many other papers in over 100 international journal and conference publications. Professor Hu was awarded the Yorkshire Forward Chair in Wireless Communications by the Regional Development Agency for her contributions to wireless communications research and knowledge transfer activities in 2007. Professor, if you please.
Thank you, Mike. Good morning, everyone. Yes. Right. So today I'm going to talk about, aeronautical communication in the connected sky. Due to the fact that actually in the past 15 years or so, we have been involved in aeronautical communications. We have been involved in many flagship projects. 2 of them are from the EU. So today I'm going to look at, first of all, the history, but this is a very brief history of aeronautical communications. And then this will be followed by, 2 of the EU projects that we were involved in. One is the wireless cabin, the other one is called Sandra. So the brief history, actually, it is whenever we talk about history for aeronautical communication, we have something called the pre-1947, because before we have radio. How does the aeroplane signal the control tower? Actually, they just use something called the wingtip dipping, so as to signal the control tower that they are approaching the runway. And obviously, this type of signal, it is unreliable, is prone to error. In 1997, we have the first successfully recorded air-to-ground and ground-to-air radio transmission. But at the same time, they still use this wingtip dipping to signal the control tower. And in the 1940s, the radio in the region of 3 to 30 megahertz, they are made available for use in all the aircraft. But however, they are not standardized. They are unstructured. So they are prone to static and atmospheric noise. So it makes it unreliable. So now it comes to 1947. This is where the actual radio communication comes into the aeroplane. They also formed the International Civil Aviation, or in brief the ICAO, on the 4th of April that year. And at the same time, they also allocated the VHF frequency band from 118 to 132 megahertz. With 200 kilohertz bandwidth. So this makes it there will be round about 70 channels available. And this was defined by the World or the World Radio Conference for Aeronautical Mobile Router Service. So this is where the radio communication era started in the aeronautical communication history. Actually, in between, there are quite a lot of activities going on. I skipped on that. But however, in 1978, we have, the airing, character-based ACARS. ACARS stand for Aircraft Communication Addressing and Reporting System. Before, the ACARS, actually, the communication between the aircraft and also the control tower, it is by voice communication. With ACARS, they are able to use the data to communicate, but at the same time, this data, they are only limited to character-based, which means that every time they just issue 1 or 2 characters. At the moment, ACARS is still, used, but, in parallel, nowadays, they are also talking about the aeronautical telecommunication networks. So in 1983, actually, this is, the establishment of the future air navigation systems, or what we call, the FANS. What they want to do, they want to define, aeronautical system, which are, more with more automation and more reliable. This, what we call, the ATN, or the Aeronautical Telecommunication Network, it is an integral part of, the FANS. And in here, 1991, we have the endorsement of the Communication, Navigation, and Surveillance Air Traffic Management concept, as well as, the ATN. So in the 1983, they were talking about it, but now in 1991, this is endorsed by ICAO. So obviously, there are quite a lot of activities going on. If we went back to 1947, we mentioned about the VHF. Actually, at that time, VHF, they have, the first data link. They have, the VHL, VDL1 as well as, VDL2. That is, the VHF data link 1 and data link 2. But the data link 1, actually, at that time, it was used for trial purpose. But in 1994, when the validation of the VDL data link, completed, they have, taken off, the VDL1. VDL2 is, adopted for information exchange between the air to ground. They use the modulation scheme of differential APSK. So VDL2 is still, used nowadays for the aeronautical communication. In 2001, what they have, we have, something called, the VDL4, that is the mode 4. This is adopted by ICAO. Basically, it is for use in the ADS-B. ADS, it means, the automatic dependent surveillance broadband transmission. It is automatic because it doesn't involve, the pilots. It will be automatically detected through, the navigation system. It is, broadcast, to all the aircraft. So, but in 2004, because the system currently that we're using is still quite backdated. In 2004, the Europe as well as in the US, they see that actually there should be modernization to our air traffic management system so as to increase the safety of air travel. So the Europe, they created this single European sky ATM research project, or in short, which is called the CESAR project. It is still ongoing. Their objective is to modernize the air traffic management system by having the different more reliable radio communication, also automation, so that the pilot by 2020 they can decide on their flight path, obviously with the aid of the navigation system as well as air to ground communication. And in 2009, actually, in between, in parallel, the U.S. they also have the next gen air transport system project. The idea is also to modernize their radar-based system to satellite-based system for use in aeronautical communication. Now, this 2007 actually this is related to the CESAR project. They have what they call the Action Plan 17. They recommended three the future communication infrastructure. Basically, they recommended 4 the airport, when the aeroplane is about to land, they would use what they call the Aeromax. Aeromax is something is an aeronautical communication system for use in service airport. It is based on the WiMAX standard. At the same time, for Continental, they recommend what they call the LDAC, that is the L-band Digital Aeronautical Communication System. Apart from that, when the aircraft is en route flying over the oceanic and also the remote region, they recommended to use satellite communication. The satellite communication at the moment, it is earmarked for the Inmarsat Swift broadband. And 2010, the European Commission, based on the CESAR project, as well as the US, they agree on looking into the interoperability issue between the EU CESAR and also the US next-gen air traffic management system. And obviously, work doesn't stop in 2010. Actually, both the CESAR as well as the next-gen projects, they have come into the implementation phase. There are quite a lot of trial and validation going on. So I'm not going to talk about that, because things will be implemented and also enforced by the FAA in future. So this is just a very brief history, and you can see that for air travel, hopefully by all these activities, it will become safer and safer. And now I'm going to talk about the two of the European projects that I myself are involved in. So the first one, it is back in 2002, which is the wireless cabin project. The wireless cabin project, actually, it is supported by the European Commission under the Framework 5. The full name for wireless cabin is the development and demonstrator of the wireless access for multimedia services in aircraft cabins. The project was carried out by a 9-member consortium. It was coordinated by the German Aerospace Center, DLR. You can see that quite a lot of big companies are involved. First of all, the Inmarsat. This is the global satellite operator, and then we also have Ericsson, Siemens, Airbus, that provide the aircraft for trials, as well as a few other SMEs. So the vision of aircraft actually comes from the fact that at that time perhaps we can still use the onboard communication, but however at that time everyone now the mobile phone is very popular. So the consortium was thinking of why can't we use our own mobile phone or own laptop so as to enable for business travel. They can still keep in touch with their company. Whether it is a good thing or not, I don't know, because it also means that you cannot escape from work while you're in the aircraft. And then at the same time, we were also thinking, okay, maybe we can provide in-flight entertainment. We can also talk to our friends and families. As Professor Ray Sherry said, maybe now we cannot enjoy a quiet flight anymore because people are busy talking to each other. Maybe later on you can see that actually this project is in Europe the first project that actually provide a voice trial from air to ground. Now the objective basically is to specify a system that is going to be installed in the aircraft cabin. Now bear in mind that this project was carried out in 2002, And at that time, we have, the third generation mobile telecommunication system, the UMTS. So we were looking into installing a picocell inside, the aircraft, that is, with UMTS. And then the Wi-Fi as well to enable the passengers to log on, to the wireless, local area network inside the aircraft, as well as, the Bluetooth. The Bluetooth was brought in, because, at that time Ericsson was developing, their mobile to home equipment. So we have, the privilege that, we have Ericsson actually implementing, the mobile, to home, equipment on board the aircraft, which makes use of, the Bluetooth technology. But eventually, we want to develop a system prototype and also to demonstrate the in-cabin communication service. Now, all these, it requires, to define the definition of the protocol stack as well as the signaling procedure. Now, for the protocol, now, because the aircraft is keep moving all the time, we have to look into the mobility management issue. We also have to look into the authentication, authorization, and accounting issue, because for users, if they want to get onto the infotainment service inside the aircraft, they have to pay. There are various pricing mechanisms defined in the project, but I'm not going to talk about this. Because they have to bill, obviously they need to be authorized and also to be authenticated before they can access to the service. Another issue that we look at is the quality of service. We are talking about multimedia communication. We need to look at the bandwidth. We need to look at the resource allocation issue. Virtual private network, as I said early on, we want to create a network on board the aircraft so that for businessmen, they can still communicate with their own organization. Apart from all these, the aircraft cabin, the propagation environment is quite different from the obviously from the propagation environment that is in the air, as well as for example in the terrestrial system. So we also want to study, because we are using Wi-Fi, whether there are any interference between the Wi-Fi as well as the electronic equipment inside the aircraft. Finally, we want to look at whether there are any interference, as I said, in the avionics, as well as the terrestrial networks when it is about to land, or to take off from the airport. Now, in here, one of the SME, they actually studied, on the type of services to be provided, by this type of communication inside the aircraft. First of all, we look at, the low data service that would include, the destination information, the news, the email, browsing the internet, in-flight printing, as well as the company network access. So these, they refer to as the low data rate. Now for higher data rates, because we want to provide the infotainment real time, so we look at the live TV, live radio, video on demand, video conference, also networked games, these type of services which will demand more bandwidth. Other services include online banking as well as e-commerce. Those are the in-flight services that we considered in the project. This is the conceptual architecture. In here, you can see that we have the wireless cabin, remote mobile network on the far left. This is actually the network inside the cabin itself. So this network, or the cabin network, is connected through the satellite network to the PSTN, our telephony network, the internet, as well as, the public land mobile network. We also consider, the Aircom network service provider that is connected, to all these networks. So when we designed, this type of network philosophy, there has been, discussion, between the satellite, operator as well as the Aircom service provider. And if you can see, from this diagram, for people or for passengers subscribing to the service, they can actually go through, the satellite network without going through the Aircom, provider. Whether this is, the debate comes in, where, the Aircom service provider, can get, for example, the subscription. The satellite network, obviously, the bandwidth is also very scarce. It is very expensive. There has been quite, a heated debate. But in reality, for the satellite, network, they have, they provide, the transport mechanism. And for this particular project, because we are only looking into the, air passenger, service, so the air, traffic management, is not coming, into sight. So the Aircom, service provider network, it is, connected, to the satellite web network. Later on, it will also be connected to the Aeronautical telecommunication network, which provides, the air traffic management service. But this is not considered in the wireless cabin, project. Now, the conceptual architecture, obviously, in the wireless cabin network, we have to, install, the network. So we divide, the aircraft cabin into several communication segments. One is, the cabin segment, and then we also have, the satellite segment and also the ground segment. Now, for the cabin segment, as I said, we implemented three, technologies. One is the UMTS, and then Bluetooth, and also the Wi-Fi. This is, all we refer it to the local access domain. And the old local access domain, actually, it is, they're all integrated by what we call, the service integration domain, which essentially it is some form of router. And the service integration domain, it is connected, to the what we call, the transport domain, which is the satellite segment. And we consider, two satellite segments. That is why we have, satellite 1 and also satellite 2, which we will look into later on. And then on the ground segment, we have the service provider domain, also, our public and home network domains that would constitute, consist of, PLMN, PSTN, and also the internet. So all these, they are connected together in order to provide, the air-to-ground, communication. Now, for the local access domain, the three technologies considered, but however, apart from that, we are also able to define user-specific local access domain. So this will simplify, the configuration of the service integration domain, because we have to set up, the different policies for individual user groups. And the same physical local access domain infrastructure, they can support multiple logical local access domain, which means that you can have, different, Wi-Fi points, access points, which, can form, different, access domain. Because you have to bear in mind that, we are talking about, Airbus, at that time we, the Airbus, at that time they are building, their very large, Airbus, aircraft, the 380. So actually there are, we need to use, more than one Wi-Fi access point. We also need to test, more than one, a picocell, for the UMTS, architecture. And we also perhaps use different authentication technologies for each user group because, for example, the passengers logging onto the Wi-Fi, they need to have different authentication mechanism which would be compatible to the Wi-Fi, as well as UMTS. We need to use authentication mechanism which is compatible to the UMTS technologies. So the local access domain will be connected to the service integration domain. So essentially, for the service integration domain, it will support multiple users communicating through one or more local access domains, which we discussed earlier. Apart from that, it will also have to schedule and also multiplex heterogeneous streams. Those streams originated from the UMTS, originated from the Wi-Fi, as well as the Bluetooth. And these streams, they are actually multiplexed into to one or several satellite terminals. That is, the transport segment. This way, we can provide, different type of service, as well as different, transport, bearers provided by the satellite. The service integration domain, it will also receive, from the satellite segment, a multiplex of applications. It decodes it and also forward, the applications to relevant networks, so that, the passengers on board, they can receive, the applications, or they can communicate, with the ground. It will route external traffic to the service provider domain through the transport network, which is the satellite network, and it will also receive traffic and signaling to the correspondent entities on board, which is very important in order to provide continuous service. Apart from all these previous function, it will provide server functionality for IP address assignment, because when the satellite moving from one network to another for the aircraft, it will go through the different networks. So there would be different when it goes through different networks or different countries, we have to reassign the IP address, so that the ground network can allocate the aircraft. It also provides the server functionality for session control, provide access to local content, and also cache functionality. Because whenever a passenger when they want to open session, they also need to establish the connection, or to inform the network that they want to establish a session. It will also select the transport network to be used for different types of traffic. For the transport network, as I said, we have the transport or satellite network 1, satellite network 2. They provide different data rates, so there is a selection between the two. It will also support the QoS, the quality of service for the carried application. That is, where the quality, the radio resource management comes into the service integration domain. So for the service provider domain, actually it works hand in hand with the service integration domain. It will provide the access control mechanism to the network and service, because for the passengers on board the aircraft, many of them, as I said before, we are looking into using our own mobile phone, our own laptop. They have their own, service provider on the ground. So the access control, we have to go through, their ground network, and then register, on board, the aircraft. But the access control mechanism, the authentication mechanism, will have to work hand in hand with the service provider on the ground. It supports the authentication mechanism on behalf of the home network service provider. It also aggregates the accounting information. As I said before, we have to bill the passengers if they want to use the service on board. It maintains mobility management function. this is where actually the IP address assignment is coming into place together with the proxy server on board the aircraft. It is also responsible for interconnecting with the public voice messaging and data networks to enable the passengers to communicate with the networks on the ground, and also convert the different media formats. For example, we have the different voice codec types as part of the interfacing capabilities, so as to allow the different types of networks, land mobile networks to be connected to the aircraft. So this is the system architecture. So you can see that actually there are quite a lot of entities in the system architecture. Particularly, we look into the cabin segment. You can see that we have the DHCP server, which is responsible for allocating the IP address. We also have the proxy AAA, that is the authentication, authorization, accounting server. This is proxy because it has to interwork the AAA server on the ground. We also have the SGSN, MSC, and also the GGSN. Those are the UMTS, core network infrastructure. We also have the SIP server, to enable a session to be established. The MGW, the multimedia gateway, this is where the codec conversion is carried out. So the cabin segment actually it works as a client to the service or the server on the ground segment. So if we look at the ground segment, we have the router which is connected, which has the location register. This is specifically created for the aircraft network, so that whenever the aircraft network moves, they will be registered on the location register. The SIP server, this is the corresponding pair, so that it can communicate with the SIP server on the ground in the aircraft. And this we also have the SS7 signaling, also the media gateway. All these they are connected to the different public and home networks. So if you look at the integration domain, this is where it starts. We have the proxy AA, the SIP server, the OMS. Actually, it is for the operation and maintenance, because all the entities will have to be managed. We also have the BSS, also as well as the media gateway. So these you can see that there are these are connected. One side to the local access domain, and the other one is to the transport domain, which is the satellites. So in the previous diagram, you can see that there are two routers. Basically, the router one, it connects all the wireless domain, so that the traffic can be integrated or multiplexed. And the router 2 will handle the traffic to and from the transport domain. That is, it will be multiplexed through to the satellite, or it will take in the traffic coming from the satellite network. So for the router 2, it will handle all the quality of service, the emission control, as well as forwarding the user data. The proxy AAA entity, actually it handles the radius signaling through which the authentication, authorization, and accounting take place. For the SIP server, basically it will enable convergence at the session level. The convergence in the sense that because we have the different radio access technology, each one of them, they have, different session establishment. So we need to find a mechanism so that, when a passenger, they want to start a session, they only need, one mechanism. And this will be, integrated into, the technology-specific, connection establishment. So the SIP session, establishment, it is used, to enable, the unified framework to establish a session in the aircraft. In conjunction with, the media gateway, it will, try to set up, the best available codec, for the cabin, according to the codec used for the satellite link. The OMS, as I said, it is the management entity. It will use, the network management protocol, for example, the SNMP, in order to probe, the equipment, in order to make sure that, everything is functioning, correctly. The BSS, this is the billing subsystem, which is used to bill, the customers if they want to use the service. So, talking about the transport domain, this is, the satellite. So we have what we call, the basic scenario. For this basic scenario, it is for small aircraft. It also caters for low data rate service, such as email, web browsing, low passenger demand, and low satellite bandwidth. You can see that, in here we use the Inmarsat Swift broadband, which provides, 64 kilobits, per second. Essentially, it is, aiming at, voice communication from the aircraft. We also have, the enriched scenario. This is, where, the SAT2 coming in. It is catered for larger aircraft. It provides more cabin service, more, bandwidth demanding. For example, video conference, live TV, network games, and so on. So we also have, more passengers. So in here, we look into, the Inmarsat, BGAN, the Broadband Global Area Network. This is, an Inmarsat 4 satellite. It provides, IP services, up to 492 kilobits per second, as well as, providing, the voice communication. We also look into, the Astra Broadband Interactive System. This provides, up to 2 megabits, per second. So this, the transport segment, communicate with the service provider segment. So you can see that quite a lot of, the entities in here, they are, the counterpart of the integration segment. We also have the OMS, which will ensure that the equipment on the ground, actually, they are functioning correctly. So we have the local, register, for the mobility management, SIP server, and also the media, gateway, connecting to all these home and also public network. So in here, the different lines, they specify, different things. The basically the dotted lines, they are for signaling. The more solid line, they are, the interface, between, the service, provider network with, the different types of network on the, on the ground segment. So for in the service provider domain, the router, it handles, the traffic to and from the aircraft, from the terrestrial networks. For the SS7 gateway, it will convert, the SS7 signaling from, the second generation, such as, the GSM and also the 3G home networks into radius and SIP messages. So later on, well, there is a diagram showing, what we use in the protocol architecture. By doing so, it will allow a standard attachment mechanism whether you use UMTS or Wi-Fi or Bluetooth, you can still be able to use one single protocol or signaling message to connect to the different networks. For the wireless cabin location register, it supports the AAA server functionality. It provides users with their temporary number so that their messages can be routed to the passengers. It will also include a user database where the attached user data is stored, so as to check whether the user is they are allowed to use the service, as well as to inform the home network where they are. The SIP server, essentially it connects, the system with the telephony network as well as the mobile, the public land mobile network. The SIP server, you can see, if you remember, in the service integration domain, we also have, a SIP server. They work together so that we can use SIP, as the convergent mechanism to enable session management, session establishment to take place. The OMS, MGW, BS, we talked about it before, when we mentioned about the service integration segment. Essentially, they are, the counterpart of the SID entities. So, in the previous slide, we have the SIP, we have the radius, we have RSVP, we also have the what we call the mobility management. So consider that in the aircraft we use all these different technologies. We don't want passengers, or we do not want to use different session establishment. We do not want to use different authentication mechanisms. That is why a main part of the wireless cabin projects is to define a unified protocol, so that when the passengers, when they are in the aircraft, they use one set of protocols rather than 3 different sets of protocol according to the radio access technology. So we have decided that in a wireless cabin, for any session request, we use the SIP, that is the session initiation protocol. For authentication, authorization, accounting, we use radius. For resource allocation, reservation, we use RSVP, and then for mobility management, we use the mobile IP. All these, they are IP protocols. So essentially, we are saying that in wireless cabin, we use the IP protocol as the convergent layer, so that every protocol we have will be converted to IP before they are going out or coming into the local access domain. So we specifically, we will look into the authentication, authorization, and accounting mechanism. There are 2 commonly referred protocol. We mentioned, radius. This is the remote authentication for dialing user service. It checks, whether a valid user customer is allowed to access, a particular service. So this is, the radius, and this is adopted in wireless cabin. But there is another one, which is, the what we call, the extended version of radius, which is called diameter. It doesn't have, a full acronym. The diameter comes in because it is an extended, radius, and that is why it is called, diameter. It has, new commands. For example, they have the built-in, extensive authentication protocol. They have quite a lot more, functionality. Radius is adopted, because it is simpler to use. That is why we use radius, at that time, in order to test, the functionality of the wireless network. This is, the authentication scenario. You can see that, we have the user equipment. It can be a laptop. It can also be, for example, the mobile phone. In here, the user, if they want to access, to the network or the service, they will, send, a, session establishment, signal using the SIP. So once, this is done, they will, look at, the use, radius to authenticate. So in here we have the local access domain. We have, for example, the access point, the Wi-Fi access point, and then in the service integration domain, that is, the router, we have, the built-in, AAA server with, the radius, implemented. Obviously, you can also implement, the diameter, but, for wireless cabin, we specifically, study, the use of radius. In the transport domain, we have, the two satellite segment. This also, on the ground, we have, the AA server, which is the main server, but the AA server on board, the aircraft, it is, a proxy server acting as a client, to the AA server on the ground. So in here, for wireless cabin, actually we have carried out, quite, a large demonstration campaign. This is, the demonstration architecture. It is similar, to what we have, in the, the system, architecture. So we have, the user equipment on board, the aircraft. In here, you can see that we have the telemedicine equipment because one of the demonstration scenario in wireless cabin, actually it is to look at, whether we can, transmit or, how telemedicine, can be transmitted, to the ground, just in case if a passenger, they fell ill, whether we can perform, this type of operation. We also have, the spectrum analyzer, to measure, the different signals, and as well as, to look at, the interference, among the networks. So the local access domain, we have implemented, the two Wi-Fi, also, 1 picocell as the demonstration architecture. All these, they are connected, to the service integration domain. So one thing, that we need to mention is also, the noise generator, because we actually want to look at, the interference, how it affects, the communication. So these actually, they are all integrated into the cabin router. We have the video server cache. We also have, the accounting logbook server. So these actually, formed, a part of the demonstration scenario. Now, in the ground segment, we have, the service provider segment. We also set up, the counterpart, on the ground. Specifically, we also have, the VoIP gateway to enable, voice over IP to be tested. We have, the AAA gateway, as well as, the SS7, gateway set up, that forms, the demonstration architecture in wireless cabin. The demonstration scenarios, that we considered is, the GSM, voice communication in the cabin. So 3 phases with, different implementation stages. We also look at, the crew communication using voice over IP. So this is, the PDAs, with, the Bluetooth handset, the voice communication, as well as, for data. We also test, the Bluetooth access, in the cabin using Ericsson's provided, mobile to home, device. We also demonstrate, the passenger authentication scenario. the cabin service control, how we can, support, the quality of service, the L and KU band satellite handover, the in and outbound, streaming, VPN, mobility control, as well as, the GSM power control. Those are the demonstration scenarios in wireless cabin. So this is, the setup showing the diagram. But you can see that, those are the equipment set up in the cabin. The ground test, the system standing test, the runway test. So before we go on to the flight trial, we actually make sure that everything is functioning correctly, and then before we actually have the flight trial. So we use the Airbus, A340, and actually one of, you can see in the far right, this is the Chinese. He is, our researcher at the time. He actually was on board, the aircraft. I have to say it is very brave of them, because all the equipment, they are test equipment, so they're risking their life, to do the flight trial. And actually, they also need to sign, an agreement before, they do the flight trial. However, for wireless cabin, actually, it is a very successful project. It demonstrates, the successfully completed flight trial of multiple simultaneous mobile and wireless technology, including GSM, UMTS for mobile telephony, Wi-Fi and Bluetooth for mobile computing service on board the Airbus, A340. This is connected to the satellite link, provided by the, Inmarsat, the Swift 64 satellite. This was carried out, in 2004. We successfully demonstrate, the first mobile phone call on the flight, using our own mobile phone. This is the first mobile phone call, in Europe. We are very proud that we make, this history. Also, we demonstrate, the authentication, authorization, and accounting, system for accessing the in-flight, services in Europe in 2004. And I'm also very proud that we actually install, the authentication server right here in Bradford. We successfully demonstrate, the web browsing and also virtual private network, which the German aerospace, the coordinator, they actually try to get access, to their network, on board the aircraft. We successfully demonstrate that, during the flight trial in 2004. So wireless cabin has been very, very successful. And actually, this prompted, the European Commission to pay attention to aeronautics, and transport. So this is, where, the Sandra project created. I'm aware of the time, so I'm going to, briefly go through my slides. But fortunately, I don't have that many, for this one. So Sandra, it means, seamless aeronautical network through integration of data links, radios, and antenna. It is a 23 million euro project. 16 million is funded by the European Commission. It is coordinated by CLEX Communication. It has got 32 consortium partners, including all the Thaleses. University of Bradford is a part of it. And Sandra aims to design, implement, validate, through in-flight trials, an integrated aeronautical communication system using an open, architecture, as well as a common set of interface and well-proven, industrial standard. This is, the vision. We want to connect to different radio access technologies. We want to provide, the different, aircraft services. So the vision, actually, it is an integration vision. First of all, there are 4 levels. One is we want to integrate, all the services, whether it is air traffic service, air passenger service, airline service, or operation service. Secondly, we want to integrate, the network, actually the architecture of Sandra, it is slightly different from wireless cabin. We want to use, IP in order to provide the unification point to allow, future legacy, technologies to be integrated together. We want to integrate, the different radios. As I show in previous slide, there are different radios to be considered. So we use the software-defined radio technology, and finally, we want to integrate, the antenna, looking into integrating the hybrid Ku-band and L-band antenna to enable, the asymmetric broadband link. These are the activities carried out, in Sandra. We look at, air-to-air communication. We look at ground-based communication. We look at airport, to aircraft communication. We also look at, using the ESA on the IRIS program, look at the satellite-based, communication. So these are the services, that we consider: the ATM, AOC, AAC, APC. This is, the conceptual architecture, and you can see that, the difference between wireless cabin and Sandra is the fact that in the transport segment, we have, several radio technology rather than just using, the satellite. It includes, the Aeromax, includes, BS2. We include, the VDL2, which is, the standard, for voice, to carry voice. So this is, in Sandra, we look at the radio resource management. So this is the functional architecture. In Bradford, we developed what we called the Joint Radio Resource Manager. This Joint Radio Resource Manager, actually, it will adapt, the different radio access, protocols to an IP protocol to enable the different radio access technology to communicate with, the different, with the router to provide, in order to provide, the different, services. So this is, the software architecture, this implemented on the demonstrated. You can see that we have what we call, the IMR, which is the integrated modular radio. This is, the software-defined radio platform. We implemented too because of the redundancy purpose. So the Sandra, it is, a flagship project, regarded by the Commission. We demonstrate, the operation of the software-defined integrated modular radio using the Airbus, A320. We also demonstrate, the successful interworking of the different radio technologies, which is, what we want to achieve, in Sandra. So I know that, I present Sandra in a rush. I'm really sorry, but, if you have got any questions, you're welcome to ask me, after, or during the break. Thank you very much, for your attention.
Thank you very much, Professor.